Okay. That's good. All right. Testing mic. Testing, testing. Okay. First, I would like to begin by apologizing to my Chemistry 101 class. The last time we met, we had only proceeded through Chapter 9, up to but not including the molecular orbital model. Today, I jumped right into, during our class today, I jumped right in review of Chapter 9 when you had not been given the particulars for the molecular orbital model. So, this is kind of out of order, but at least it will be recorded and available on Blackboard for your review. So consider this part 2 of Chapter 9, Covalent Bonding. The molecular orbital model. In contrast to the localized electron model, which assigns electrons, either lone pairs or bonding electrons, to either particular atoms or to bonds between two atoms, the molecular orbital model takes all the electrons that are assigned to a molecule and spreads them over an orbital system that is particular for that molecule. This process is akin to delocalization of the electrons that we alluded to in the part 1 of this chapter's discussion. Delocalization of electrons can follow from the lost my words. Delocalization, let me start over. Delocalization of electrons can be thought to follow from the concept of resonance, where you have two or more valid Lewis dot structures that must be given equal priority. Therefore, the electrons are assumed to spend time in each form, but they're still localized. Delocalization in the molecular orbital model, however, effectively smears those electrons over the entire molecule. And the process of delocalizing electron density in bonds or in lone pairs adds to the stability of the molecule. Anytime you can give electrons more elbow room, it stabilizes the molecule. Okay, There are two types of bonds that can be characterized for molecular orbitals. The sigma bond has its density localized on axis between the atoms. Come on, there we go. So here's an example. If you have two protons coming together, say for instance in dihydrogen, right? These would be then hydrogen, and the density of electrons we would assume to be largely between the hydrogen atoms. But they don't have to be there. In the molecular orbital model, they could just as easily be out here, not between the atoms. As a practical matter, if the density of the electrons is between the atoms, we say those are bonding molecular orbitals. Whereas if there's a node between the atoms, then the electron density is spread out opposite that node, and those are anti-bonding orbitals. For dihydrogen, there's only one bonding and one anti-bonding molecular orbital. Let's see. Yes, we are going to get the description. This is the best way to describe it, to actually show you the construction of molecular orbitals. If we assign energy along this axis, and these are the individual atoms here, the two hydrogen atoms, that are going to come together to bond as an H2 molecule. Then we put the atomic orbitals here, which would only be 1s with one electron, 1s with one electron for this one. And then we combine them. When you mix those orbitals, you get the same number of molecular orbitals as the atomic orbitals you started with. So if you start with one atomic orbital for each atom, then the molecular orbitals, once the molecule is established, then you get two molecular orbitals. One of those molecular orbitals in this case will be lower energy. That's the bonding orbital. Lower energy than its original atomic orbital. And there will also be an anti-bonding orbital. So let's just draw this the way I would normally do it. And there's only a slight difference between the way I draw molecular orbitals and the way the authors of your textbook do. But the rules are still the same. Two atomic orbitals, two molecular orbitals. So this one is a sigma formed from the 1s atomic orbitals. This is a sigma star, which is our designation for an anti-bonding orbital at a much higher energy level. So we start off with this many electrons, then we take those two electrons and we populate the molecular orbital. We do it the same way that we used to do with Hund's rule. In other words, we fill the lowest energy first, work our way up, and we can only pair electrons once we have filled all the degenerate orbits, that is, those at the same energy, with singular electrons. So since there's only one, then we can pair the other one like that. Now we have the molecule with its molecular orbitals, and we find that both of them are in a bonding orbital. So both of those electrons are exhibiting electron density that is on axis between the hydrogen atoms. And even though the anti-bonding molecular orbitals do exist, there are no electrons occupying them at this time. Okay. The molecular orbital model, of course, has to abide by certain rules, and it has to explain various molecules that are thrown at it. And that being said, the electron distributions and energies that are present in the molecular orbitals that are occupied by these electrons agree with energies and bonding characteristics. Typically, the sigma bonding orbital is going to have a density on axis, like this. The anti-bonding orbital sigmas will be sort of like this, with a node in between. Remember what a node is. A node is a plane where there is zero probability of finding electron density. Okay? We're going, the reason I emphasize that is we're going to discuss a second type of orbital that has electron density off axis. And that will come in just a few minutes. Molecular orbitals are like atomic orbitals in that each one can hold 2 electrons of opposite spin. So that has not changed from our earliest building of electronic configurations for atoms.
An s orbital has a spherical shape. S orbitals on different atoms can combine to form molecular orbitals. As 2 hydrogen 1s orbitals approach one another, the orbitals combine with an increased electron density between the atoms. The result is a sigma bonding orbital. S orbitals on different atoms can also combine by subtracting the 2 1s orbitals. A decrease in the electron density between the atoms is observed, resulting in the formation of a sigma antibonding molecular orbital.
Okay, the concept here between addition...
An s orbital has a spherical shape. S orbitals on different...
the idea here is similar to constructive and destructive interference. When light beams cross, if they have the same frequency, for instance, right? So you have wavelength, and so many waves passing a point in a second gives you frequency. Then if you have another one, another light beam of the same frequency, the same wavelength, superimposed in phase with this one, right? Just like that, it matches up perfectly. Then the intensity is additive, like that. So the addition of those 2 waves gives you this. But if they're out of phase, so the other one comes in like this, like that, has the same wavelength, it's the same frequency, but it's out of phase by half a wavelength, then the result is destructive interference. And they cancel one another out. Okay? So that's not a one-to-one relationship with bonding versus anti-bonding orbitals, but the concept is similar. constructive interference versus destructive interference, produces either bonding or anti-bonding orbitals. The mathematics is quite a bit more complex, so we're not going to deal with that here. The concept is the more important. Now, a useful calculation, once you've got the molecular orbital, a useful calculation is called bond order. Bond order is simply the difference between bonding versus anti-bonding electrons divided by 2. So in this case, the bond order for dihydrogen would be 2 for the bonding minus 0 for the anti-bonding divided by 2 equals 1. So the bond order of dihydrogen, H2, is 1. Sometimes, when the bond order is a whole number, we can sort of allude to, but it's not strictly kosher. If you have 2 hydrogen atoms bonded with a single bond, because remember this line represents 2 electrons, right? Then a single bond is bond order of 1. Whereas a double bond between oxygen would have a bond order of 2. And that is true. But it's not a one-to-one correlation. I mean, you can't just say that every time because bond orders can have fractional values as well. But it is true that the higher the bond order, the stronger the bond. So we're going to look at some other examples here in just a minute. But that's one of the few calculations that we have that are required in this chapter is bond order. So here we have H2, as I've drawn it here, with our bonding, anti-bonding. Both electrons are in the bonding. Bond order is 1. Okay, we've done that. Now, what happens if you add an electron to that molecule? Where does it go? Well, it goes to the next energy level, so it has to go here, right? So what's the bond order now? Well, it's 2 minus 1 anti-bonding divided by 2 equals 1/2. So by adding an electron to this molecule, we have weakened the bond from a 1 to a 1/2. While we're at it, what would happen if we subtracted an electron? It would have to come from here, would it not? And that would make it an H2 plus. So in that case, we would have a 1 bonding minus 0 antibonding divided by 2 is 1/2. So in this case, whether you add an electron or subtract an electron, you get a weakened bond. That's not always the case. It depends on the molecule. Remember, these molecular orbitals are specific to each molecule. All right, what we've discussed so far up to this point are homonuclear diatomic molecules. That is, they're diatomic, that is, they're 2 atoms bound together in a molecule. And they're homonuclear, that is, both of the nuclei are identical.
When 2p orbitals are aligned sideways and added, a pi bonding molecular orbital is formed. When 2p orbitals are aligned sideways and subtracted, a pi anti-bonding molecular orbital is formed.
Okay. So now we're getting to, we've introduced another type of bond. These are sigma bonds. And remember, the electron density for a sigma bond is on axis between the atoms. The electron density for a pi bond is off axis, but it has no nodes. no nodes between the atoms. It's simply off-axis. Why is that? Because you can't have a pi bond without a sigma bond. So there's your sigma, here's your pi. You always have a sigma before you have a pi, and you can have more than one pi. We turn this around and look at it right down the chute, then we're going to have sigma bond density this way, but pi bond density this way. That means that you can have a pi bond here. You can also have another pi bond over here. So between two atoms, you can have one sigma bond and you can have two pi bonds. Just stick that in the back of your brain and hang on to it for a while. It will reoccur. Okay. So how do we get a pi bond? Well, there's a reason, and there's one good reason why the molecular orbital theory was proposed in the first place. There was an observed characteristic of various molecules that could not be explained with a localized electron model, no matter what you do to it. So remember what we do when a model fails, right? We either modify, which was not available for the localized electron model. There's no modification we could make to the LEM that would explain these characteristics. So we could also just ditch it, just throw it out, right? Start all over again. Well, the localized electron model has value. It does explain some things. So we're going to hold on to it, and we use our third option, which is we restrict its use. So the localized electron model is restricted in use, and whenever we encounter these two characteristics, either paramagnetism or diamagnetism, which I'll define in a second, when we encounter those, we just automatically use the molecular orbital model because the localized electron model is restricted. It cannot enter this territory. Okay, so how do we explain this? First of all, what's the definition? Paramagnetism is characteristic of a substance that's attracted into a magnetic field. Diamagnetism is a substance that is repelled or not attracted to a magnetic field. Right? So why is that? Well, the simplest explanation is the paramagnetic material has at least one unpaired electron. So you think of an electron as a little spinning negative ball, right? So it's spinning around like this, around its axis. And when you get a spinning charge, a moving charge, it generates a magnetic field. So it's spinning this way, it generates a magnetic field. That magnetic field then can interact with an external magnetic field, which it does, if it is not canceled by another electron with which it's paired, spinning in the other direction. Remember, if you combine two electrons, if you pair them in an orbital, atomic orbital, molecular orbital, either one, when you combine these two, the magnetic fields are opposite because the spins are opposite. They cancel one another out. There's no interaction between this pair of electrons and a magnetic field. So if your molecule has no unpaired electrons, in other words, all of its electrons are paired, then it will not interact with a magnetic field. Whereas if it has one or more unpaired electrons, it will interact with a magnetic field. If you've ever seen these big horseshoe magnets, they're huge, and that's about the right size. Like this, like that, and they might have a little disc there, a little disc there, and there's a strong magnetic field in that gap. If you take oxygen, liquid oxygen, because gaseous oxygen will pour, right? So liquid oxygen, you pour it in here, it sticks right in that field until it's full, of course. But you pour it in there and it stays there because dioxygen, O2, has unpaired electrons. So it interacts with the field. So what happens if you do that same thing with liquid nitrogen? Straight on through, no interaction. That means all the electrons in dinitrogen are paired. If we try to use the Lewis dot structure for dioxygen, it looks like all the electrons are paired, but they can't be. They can't be and interact with that magnetic field. So we need another explanation, and that explanation requires the molecular orbital modeler. Okay, well, this is what you can measure that paramagnetism by just lowering your sample into the strong magnetic field, and this very sensitive balance will measure the attraction as it approaches. So it's quantifiable, easily quantifiable. All right, so that's not the best one. Let's go to the next one. There we go. These are molecular orbital structures for the diatomics, starting with boron, the homonuclear diatomics, diboron, dicarbon, dinitrogen, dioxygen, and difluorine. This is what their molecular orbitals look like. Now, these two over here, dioxygen and difluorine, the S and the P orbitals of which the molecules are made are far enough apart in energy that there's no interaction between the two when they go in and mix, when they go in and make molecular orbitals. Whereas the S and P orbitals here, for the diboron, dicarbon, dinitrogen, their energies are close enough so that you get mixing between the S and P orbitals, and that changes the order of the sigma and pi bonds. Let me illustrate. So for dioxygen, we have the two oxygens here, and for simplicity, we're going to eliminate, we're not going to use the 1s orbitals, because the 1s's are the same for every one of them. So we'll just leave the 1s's out and focus on the second period electrons. So for oxygen, we've got 2s and 2p orbitals. So here we've got a 2s and a 2s for this one, right? Those are atomic orbitals that we're going to use to make molecular orbitals. And then here at a higher energy level are the 2p's. 1, 2, 3. 1, 2, 3. Okay. These two S's come together and make just like our dihydrogens, except these are principal quantum number 2 instead of 1 for hydrogen. For oxygen, it's 2. So here we have a sigma orbital composed or derived from a 2s, and here we have a sigma star derived from 2s. For these p orbitals, you can only make one sigma out of each atomic. So we get one sigma here derived from a 2p. And then we get one sigma here, sigma star, excuse me, derived from a 2p. So that means we've used 2 of them, 1, 2. Now we have 4 left over. So we have 2 here, 2 here. These are pi derived from 2p. These are pi stars derived from 2p. Okay. Okay. So now, first of all, let's check to be sure we have the right number. So we started off with 1, 2, 3, 4, 5, 6, 7, 8. So we have to have 8 molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8. So that condition is met. This is how molecular orbitals look when there is no sp mixing. You have the sigma here, sigma star there, and the pi's in between. Pi here, pi star there. If we had mixing, which we do with nitrogen, carbon, and boron, then these two flip because there's interaction between these S's cause this one to be lower in energy than that one. But for oxygen, there's no mixing, so this is the proper arrangement. Now, what did we start off with? Well, in the second period, we have 1, 2, 3, 4, 5, 6. We have 6 electrons. Of course, oxygen has 8 total, but 2 of them occupy the 1s. So they would be down here, and we're not concerned with those right now. So that oxygen also has 6, and these are valence electrons. Remember what valence means? Electrons available for bonding. That's what we're doing with them. We're bonding with them. Okay, there they are in their atomic orbitals. Now we have 12 electrons that have to go into molecular orbitals. They do that just like we did with electronic structure for atoms. Lowest energy first, work your way up. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, we can't pair them until we've put 1 in each one, just like electronic structure. Now, this explains why oxygen, dioxygen, is paramagnetic. There are your 2 unpaired electrons. They're both spinning the same direction, and they interact with magnetic field. That explains molecular orbital theory, explains paramagnetism in oxygen. Okay? Before we do that, let's talk about bond order. What would be the bond order for this molecule? Bonding electrons minus anti-bonding. So bonding, 2, 4, 6, 8. Anti-bonding, 2, 3, 4. Divide by 2. There's your 2. Bond order of 2 for dioxygen, which corresponds, roughly speaking, to a double bond. Okay, what would happen if we added an electron to this molecule? Right? Just add an electron, where would it go? It would go the next highest level, it would have to pair. It would still be paramagnetic because we have 1 unpaired electron. But what effect does it have on the bond order? Well, let's see. What has changed? 2, 4, 6, 8. That didn't change. Antibonding. 2, 3, 4, 5. So that's 3 divided by 2 is 1.5. So the bond order is 1.5, not 2, which means by adding an electron, we have weakened this molecule. The bond is weaker. I know what you're thinking. What's he going to do next? Well, next time he's going to take away an electron. So I'm going to take that electron away. And it used to be like that for dioxygen. You take away an electron, comes away from the highest energy level. So now we still have 8 bonding, right? 2, 4, 6, 8. But now we only have 1, 2, 3 anti-bonding. So that's 5.5 equals 2.5. So by removing an electron, we have strengthened the bond. Okay? What if we take away 2 electrons? Right? That one would come from here. That means now there are only 2 anti-bonding electrons right here. So 8 minus 2 is 6 divided by 2 is 3. So by taking away 2 electrons, we've strengthened the bond even further to a bond order of 3. Okay. Now, if we were to do, say, dinitrogen, let's go ahead and do that one since we're here. So there's our nitrogen original atom. There's dinitrogen. Let's see. Let's take away these electrons for now. We'll put them back in as we need them. Okay. These molecular orbitals stay the same, but these are going to change because dinitrogen experiences sp mixing. There we go. See, we just flipped. This used to be up here, that used to be down there. Now, how many valence electrons are in nitrogen? We just count from the left. Nitrogen is 5 over. Each one has 5. Right? So that means we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 5 electrons in the original atoms. Now we've got 10 electrons to place in the molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we know that dinitrogen is diamagnetic. It does not respond to a magnetic field because all of its electrons are paired. Okay? You can do that with any of these and justify paramagnetism versus diamagnetism for each one. The homonuclear diatomic molecules are fairly simple to construct as long as you take the sp mixing versus no sp mixing into effect. And in your review document, at the very end, I include both this table and the one preceding it. This one. This one does a better job of explaining the mixing effect. So here, between nitrogen and oxygen, you get this shift right there, where there's no longer any mixing. Mixing occurs up here. no mixing down here. But as far as building your molecules and placing the proper molecular orbitals in place, use this one. And this will be available on the test as well. So you don't have to memorize that effect. You just have to know how to use it. Okay, what's next? Shorthand. There's a shorthand way to write this, and it's fairly simple. You just take these molecular orbitals and flip them on their side. So you put this one first, second, third, fourth, and so on. So for dinitrogen, we would write, and in this case, we would have to include the 1s orbitals as well. So the S, excuse me, let's try that again. The sigma orbital derived from the 1s and the sigma star derived from the 1s. Then we go to this one, sigma derived from the 2s, sigma star derived from the 2s. Then pi derived from the 2p, the sigma derived from the 2p. And I'm going to have to go down here. But we don't need any more, right? Because we've run out of electrons. Right? So that's as far as you need to go. But we need to put our electrons in there. So they go in here just like we did with our electronic structures for atoms. They go up here. So sigmas can hold 2, 2, 2, 2 maximum. 2, 4, 6, 8. And then we have 2, 10. Oh, we got 4 extras here. So this is 2, 4. And this is 8 and 10. Why do we put 4 in the pi's? Because there are 2 orbitals there. 2 and 2. 2 and 2. Right? Sigmas can only hold 2. Pi's can have 2. They have 2 degenerate orbitals, same energy level. So what happens to nitrogen if we add an electron? Make it like that. What happens? Where does it go? Well, now we need a pi star derived from the 2p, right? And we got 1 electron that goes in there. That 1 electron means it's unpaired. So now this one becomes paramagnetic. If we add another electron, it would go in there, unpaired, still paramagnetic. What happens to the bond order? Well, let's first do the N2 bond order. Okay. 2, 4, 6, 8. 8 bonding electrons. How many anti-bonding? Only 2. Divided by 2 equals 3. So the bond order of dinitrogen is 3. What did we do just a minute ago? We added an electron, right? So it would go in here. So that means now we have 3 anti-bonding. So 3 from 8 is 5. That's 2.5. We have weakened the bond by adding an electron. We add another electron, it's also antibonding. We'll weaken it further. What if we subtract an electron? Where does it come from? From the highest energy level. Right? So now we have 2, 4, 6, 7. 7 bonding minus how many anti-bonding? 2. So that's 5 divided by 2 is 2.5. So if we add an electron, we weaken the bond. If we subtract an electron, we weaken the bond. All right, so what's next? Heteronuclear diatomic molecules. If homonuclear diatomic molecules have the same atoms, elements, in each position, bonded together, then heteronuclears have different atoms. For example, carbon and oxygen. Now we're starting to get more complicated. With the homonuclears, we're starting off at the same energies here. So deriving energy levels for the molecular orbitals is a fairly simple, straightforward procedure, as long as you take into account sp mixing if required. When we get to heteronuclear molecules, the starting energy levels are going to be much different. Carbon's going to be a higher energy level than oxygen, simply because carbon has fewer protons than oxygen. So the energy levels are not going to be drawn as close to, the orbitals won't be drawn as close to the nucleus as they will be for oxygen. So we start off with S and P here, S and P there, and then we get, what do we get? We get a sigma. I know it's hard to see. We get a sigma from the s orbitals, and that should be 2s. Did I put, yeah. That should be 2s. So we get a sigma from the 2s, then we get a sigma from the p's, then we get pi's from the p's, then we get a sigma star and a pi stars. So in this case, carbon and oxygen, the dicarbon would be experiencing sp mixing, the dioxygen not. So the question is, which dominates? You know, which one is responsible? Is there mixing, right? Well, it appears that the sigma is where it needs to be, except that now the flip is on pop. So what do you know? Is that sp mixing? I don't know what they call it. But it's not something that I'm going to expect you to reconstruct. The reason being, it's much, much too complicated for a general chemistry class, for non-chemistry majors. Right? So this is just to illustrate that as long as you know the order of the molecular orbitals, then you can fill them in with electrons and deduce some characteristics. In this case, we have all paired electrons. This molecule, carbon monoxide, is diamagnetic. It does not respond to magnetic field. How about HF? Right? Well, hydrogen has a much higher 1s orbital here than the 2p orbital that's going to be used to bond with the hydrogen. Right? So you get the sigma here and the sigma star there because we only need one bond, because hydrogen has no, it can't bond with any more, with any others. It has to be only 2 molecular orbitals. And we use the p orbital here because it is the outermost orbital for fluorine. The 2s doesn't even come into play. So the other thing that we witnessed is that the electrons here in this atom are at that energy level. The electron here in fluorine is that energy level, but the molecular orbital is lower energy level, so it should be a stable molecule, and in fact it is. Bond order would be 1, right? 2 minus 0 divided by 2 is 1. So that stability, that lower energy level here, notice all these electrons are aggregate lower than these, right? None of them exceed the energy level of this highest level. So that implies stability for dinitrogen, in addition to the stability that's implied by the bond order of 3. Now, granted, the electrons occupy that sigma molecular orbital, but we still have a stronger pull on electrons from fluorine than hydrogen. So the molecular orbital is somewhat density shifted toward fluorine. That is still a valid conclusion from the localized electron model and electronegativity differences between fluorine and hydrogen. Delocalization. Okay. So now, this was mentioned at the very beginning of this part 2 lecture. Delocalization. The delocalization appears most pronounced in the pi bonding orbitals. And that's largely due to the fact that sigma orbitals are, we might say, trapped between, yeah, that's not working very well. Let's try another one. The sigma orbital tends to trap electrons between. So it's difficult to delocalize those. But the pi density is off axis. And it's easier to shift those electrons one way or the other if you're bonded to something else over here. Perfect example is benzene. The benzene molecule looks like this. Everywhere you have a convergence of lines here, 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 that represents a carbon atom. We just don't draw it in. Typically, we don't even draw the hydrogens in, but we're illustrating a point. So resonance for benzene would put double bond here, 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 and here, but over here, we would shift them around. They would just move one place counterclockwise, and you would get the resonance between these two. Well, that's the localized electron model talking. Delocalization and the molecular orbital theory have to account for the fact that each of these bonds is exactly the same length, which means they're the same strength. So if they're the same strength and the same length, they cannot be pi bond here and only sigma there. The entire molecule has partial double bond character. We could draw it like this. Right? So each bond is equal. Or very often we draw it like this. Just as a shorthand way, that shows that all the bonds are equal in the benzene ring. But delocalization occurs if we turn the molecule on its side like this, so we have a plane here, then we have these unused p orbitals all the way around the molecule, and the electrons are shared in a smeared, delocalized arrangement around that ring. That's why the benzene ring is so stable. It is a strong structure, very strong. Okay. Now, if we sort of slide back into the localized electron model and hybridization, we notice that each one of these carbons, if we use the localized electron model, okay, then at each one of these carbons, we have how many groups? Well, there's a hydrogen there at each one, So that's 1, 2, 3, right? And 3 groups equals what? BSEPR says it's trigonal planar. And trigonal planar is interpreted with hybridization as sp2 hybridization. Right? So an sp2 hybrid orbital in the localized electron model explains this, and then that gives you all your sigma bonds. Then your pi bonds are formed by the unused p orbital, the unhybridized orbital, which overlaps with the electrons being spread out over the entire molecule. And this is one way to represent it. You know, donut on top, donut on bottom.
The p orbitals used to form the pi bonds in the nitrate ion overlap with one another to provide a delocalization of the electrons over the entire ion.
This is true. Now, we're going to take all that information. Well, we already have looked at some of it. And it's my fault because I didn't remember that we had not yet covered this. So when we did our review today, I was talking about topics that we hadn't even introduced yet. So hopefully, once I notify the class, they'll be able to go back and look at this lecture, part 2, with the molecular orbital theory, and then the problem set that I give you to work will make more sense, hopefully. If not, we still have one more review before the last exam, and we can hash out the problems there day after tomorrow. This one, I'm not going to put a lot of weight on this one. The photoelectron spectroscopy is a method by which we can actually measure the energies of these molecular orbitals. Right? So we get a spectrum here, and each one of these peaks is associated with an electron transfer between the infinity, which is 0, ionized, and the return to each of the molecular orbitals. So we know what the energy level is for each one of these. This is confirmation for the construction of molecular orbitals, because atomic orbitals in the localized electron model do not correspond with these energy transitions. Only the molecular orbital can explain these energy transmissions through photoelectron spectroscopy. Okay, that's it. So I feel better now that I've got this on tape, so to speak, and will be posted to Blackboard very shortly.